Mohan sir, shall we start the session, sir?
Yes, ma'am. Pan, ma'am, are you ready?
Yes, yes, sir.
Yes, ma'am.
Okay, sir. A pleasant morning to all the beautiful souls over here. On behalf of Department of English, Department of Physics, PPG College of Arts and Science, Coimbatore, and the Indian Association for Crystal Growth, and on my own behalf, I welcome you all for the third day of Virtual Faculty Development Program on Recent Trends in Solar Cells. And the topic of today is one-dimensional nanostructures for solar cell applications. Now, I would like to invite Mr. C.V. Banupriya, Assistant Professor, to welcome the gathering.
A warm good morning to one and all present here. Respected principal, management, trustee, invited speakers, professors, researchers, and participants. A happy morning to one and all present here. I feel esteemed happy to welcome you all for the third day of our virtual faculty development programming on recent trends in solar cells, organized by Department of Physics, PPG College of Arts and Science, Coimbatore, Tamilnadu. It's my privilege to welcome the management of PPG Group of Institutions who has provided the constant support and encouragement to organize the program. Welcome you, sir. It gives me immense pleasure to welcome our beloved principal, Dr. N. Muttumani Madam, who always been the motivator for all us to this session. Welcome you, Madam. I wish to express my warmest welcome to Dr. K. Sethuraman, sir, Associate Professor, Department of Material Science, Central University of Tamilnadu, Thiruvarur, India, who is going to share his knowledge with us. Welcome you, sir. It's my pleasure to welcome all the participants from various parts of the region who are here to attend this virtual faculty development program. I extend my welcome to all the faculty members, my fellow colleagues to this FDP. I hope this session will be beneficial and knowledgeable to you all. Once again, I welcome you all for the third day of our FDP. Thank you. Have a great day ahead. Thank you, sir.
Thank you, ma'am. I would like to invite Dr. V. Mohan Kumar, Head Department of Physics, to introduce the guest of the day.
Very good morning to all. It's my privilege to introduce our today's speaker, Dr. K. Sethuraman, Associate Professor, Central University of Tamilnadu. He got his doctoral degree from Anna University in 2008. He started his teaching career as a lecturer in SKS Arts and Science College, Thiruvananthapuram. Later, he joined Assistant Professor in KFNSC, Konkuk University, Seoul, South Korea. Then he moved to Department of Physics, Madurai Kamaraj University as an assistant professor. Currently, sir working as an associate professor, Department of Material Science, School of Technology, Central University of Tamil Nadu. His research experiences are metal oxide nanostructures, chalcogenide nanostructures, thin film, two-dimensional layers, graphene, metal di-chalcogenides, graphene, metal oxide composite for sensors, photo and heterogeneous catalytic applications, organic electronics, organic crystal growth using solution and melt technique. Under his guidance, 8 doctoral degree awarded and 2 scholars doing PhD. Also, he has guided 20 MPhil scholars and more than 20 postgraduate students. He has published more than 85 research papers in international peer-reviewed journals. He has investigated 4 research projects as a principal investigator, worth rupees 65 lakhs, funded by various organizations like UGC, 12th Plan, DAE, BRNS, CSR. Another project sanctioned by IUAC, New Delhi. He organized 4 seminars and he has delivered invited talks in several conferences. Dr. KSR is a recipient of several awards and recognition. To name a few: Junior Research Fellowship, Department of Science and Technology, Government of India; Senior Research Fellowship, Department of Science and Technology, Government of India; Japanese Government Fellowship, MEXT for 2 years; Department of Electrical Engineering, Aichi Institute of Technology, Kyoto, Japan; Assistant Professor, 1 year, 1 month, KFNSC, Konkuk University, Seoul, South Korea; and UGC sponsored Raman US Postdoctoral Fellowship, 1 year, Center for Material for Information Technology, University of Alabama, USA. He has visited USA, Japan, South Korea, and Singapore for research collaborations. With this brief introduction, I request Dr. Sethuraman sir to take over this session. Thank you.
Thank you, Mohan Kumar. Thank you for a nice introduction. Good morning to all. So my presentation is visual to yeah?
Yes, sir.
Okay. My audio also clear, yeah?
Yes, sir.
Okay, thank you. Thank you. So good morning to all. Once again, that I today the topic of the presentation is a one-dimensional nanostructure for solar cell applications. So, of course, that preparation of one-dimensional nanostructure. Generally, people used to think that resolution technique in powder somehow it's very easy compared to that of forming a one-dimensional nanostructure in thin film one-dimensional nanostructure by simple solution technique. So that in this presentation, I would like to discuss about how simply we can control the parameters in a solution, simple solution technique, and to grow a beautiful one-dimensional nanostructure for different solar cell applications like dye-sensitized solar cells and quantum dot sensitized solar cell especially. So this is the plan of my presentation. Almost I would like to give some introduction about solar cells, and just divide that the presentation into three main categories. One is how we prepare the key to nanorods by simple hydrogen technique using a seed layer on a bare glass substrate. So how we get lengthy and number dense semi-crystalline CO2 nanorods, and the preparation of zinc oxide nano as well as the micro rod arrays, microcrystalline thin films by using an MN doping, and copper ions. How the third one is the copper ion. How copper ions induced a reorientation of the crystallites in zinc oxide nano micro rod arrays. How copper ions are playing an important role to morphological changes induced in the zinc oxide nano micro rod arrays. So all the three parties that we are just using a simple solution technique, and maybe we will see in detail one by one later. So finally, summary. Of course, that energy, generally I used to give that some introduction about that energy, why we need an energy. So energy needed for quality of life, ever increasing energy demands of the population, and the threat of climate change is stressed out the need for the renewable energy productions, and also that our fossil fuels, burning fossil fuels is today's main energy sources. That's why that ongoing depletion of these non-renewable sources. People always think about that alternative energy. So it is imperative to develop alternative technology using renewable natural sources. So one of these is sunlight, so which given its availability offers a huge potential. So that's the reason, and of course we are getting a huge amount of energy from some almost 1,20,000 terawatt of energy we are receiving from sun. Basically, we need 30 terawatt of power. So solar cells. Why solar cells are likely to provide a significant factor of power? Solar cells are safe. The trend signs we need that energy we will get. So energy reaching the earth is incredible. Support by by one calculation, that 30 days of sunshine striking the earth have the energy equivalent to equivalent of the total of all planet fossil fuels, both used and unused. So using solar energy instead of burning coal to generate electricity is much easier way to reduce the carbon emissions than replacing gasolines in vehicles. So people always think about to develop a solar energy conversion. Of course, this is the energy then we are receiving from the sun almost 3 to 10 to the power of 24 joule per year. It is about 10,000 times more than that of the global population consumption. So, if we can cover about 0.1% of this total earth area with solar cells, then we have a 10% of efficiency, then the energy produced to satisfy our current demand. So, these are just the electricity generation by energy source. This one is based on the year 2017. Now they have much improved. So majority of the electricity generation from the oil and gas and coal, and then so only small percentage of that electricity generation by the solar photovoltaics. So people always are trying to improve the solar photovoltaic electricity generation year by year. So with the updated technology. Solar cell is a basic introduction about solar cell. So basic idea of a solar cell is to convert light energy into electrical energy. A solar cell is a very large level. Electrical energy is stored in electromagnetic fields which can make a current of electrons flow. It supplies voltage and the current to a resistive load and then recognized parts of the solution to the global need for electricity and the clean energy. Solar cells are silent, and then we don't need any maintenance, and no fuels and no emissions from the solar cells. So that's the reason people always think about the solar cells. History of the solar cells, and then in the year 1839, photovoltaic effect was discovered by Edmund Degrelle. Later, the first silicon solar cell by the Bell Lab, by the three professors Chapping, Fuller, and Pearson, they achieved the power conversion efficiency of 6%. So in 1986, the heterojunction organic based solar cells they have fabricated by the Professor Tang et al. From the Eastman product company USA. So where they have used a completely organic molecules to as an organic molecules layer as a major layer for the solar power conversion. Later, the highest for in 2007, the highest solar efficiency they have achieved in Petrol Lab. They have reported about 40.7% in multi-junction terrestrial concentrated cells using metamorphic and lattice matched 3-junction solar cells they have fabricated. They have achieved more than 40% of efficiency, multi-junction solar cells. And then for organic solar cells, they have achieved that 5.7% in the year 2007. But later, and recently, they have improved it almost more than near to that of 19% efficiency from NERL. In 2020, sorry, this is 11, this is 2021. 2021, the highest efficiency we have achieved in lab scale for a monocrystalline silicon is about 26.7%, and polycrystalline about 22.3%, and the CAGS based solar cells are about 21.7%, and cadmium telluride is about 21%, and amorphous silicon is about 10.2% in a lab scale they have achieved. Industrial is a bit lower than that lab scale, of course, due to the tough panel and then production. And then, so that somehow the power conversion efficiency is less compared to the lab scale. Photovoltaic cells, solar cell is a basic building block of a solar photovoltaic, and then it is a solar cell generally. model. What is model? And these solar cells are connected together in series and then encapsulated into models. So these solar cells is connected together in series and encapsulated into models. We used to call it as a photovoltaic model. So that those photovoltaic models are connected and then parallel and the series and then forming a photovoltaic arrays. So photovoltaic array is integrated in the system with the components for charge regulations and storage. So this is a photovoltaic array. So the photovoltaic array connected with the battery backup system, and then load is given to the commercial domestic purposes. So this is some basic of the what is solar cells models. What is a photovoltaic models and photovoltaic array? How the photovoltaic arrays are integrated in the system with the components of charge, regulations, and storage. Generation of solar cells, of course, everyone is know the 3 generations, and then first generation silicon-based solar cells, large and non-flexible with the high manufacturing cost. Silicon-based solar cells are still dominant in the market. Almost 83% of solar cells are still we are using only single crystalline or polycrystalline silicons. So due to their higher efficiency in industrial, in solar photovoltaic panel, and so that is the reason still people are using a silicon-based solar cells, even though that there are enormous developments in dye-sensitized and perovskites and all types of solar cells, based solar cells. For commercial applications, people are using a silicon-based solar cell. Still, 85% of the markets are different from silicon-based solar cells. Second generation thin film solar cells, amorphous silicon, nanocrystalline silicons, and they carry telluride. In second generation, people started to fabricate in flexible substrates as well as their second generation solar cells are significantly cheaper, but with much lower efficiency compared to that of silicon-based solar cells. Single crystalline silicon-based solar cells. Third generation, newest generation solar cells are still in the research phase. Then in this generation, people used to say that dye-sensitized solar cells are polymer solar cells, organic solar cells, organic small molecules, organic and polymers. They have used to fabricate organic small molecule and polymer-based solar cells. Organic solar cells are much cheaper in production, but the efficiency-wise, we cannot compare it with the silicon-based solar cells. Still, in all the solar cell research or in research phase, so that and also recently that perovskite solar cells, and still perovskite solar cells are in the lab scale only. In R&D level only they are developed. Then not yet they commercialized the perovskite solar cells for the commercial and industrial purpose. Today talk is the completely about that how we can control the one-dimensional nanorod. Nanorod growth of that important materials like a TiO2 and zinc oxide. So it is how it is highly useful in dye-sensitized solar cells. And then this is the general structure. Of course, everyone is know that glass substrate and FeO anode, and then tie a TiO2 nanoparticles. So so stored in a dye, and then electrolyte is between FeO and FeO anode and FeO cathode and glass substrate. So instead of using TiO2 nanoparticle, and the TiO2 nanorods are very good. So by using a TiO2 nanorod, one-dimensional structure, so the electron, charge carrier injection efficiency is very good to the electrode. That's why people are always looking for the nanorod structure. So instead of using a nanoparticle, so they have that very good and better efficiency compared to the TiO2 nanoparticle in solar cell structure. Simple understanding the current DAC that earlier we used to say that nanoparticle network, mesoporous field of nanoparticle network. So that is not so good for the efficient charge injection into the electrode. So due to that of a slow electron transport of the nanoparticle network, so people always think about that one-dimensional nanostructure and growth instead of using a TiO2, nanoparticle structure. So TiO2 is playing a very important role in dye-sensitized solar cells. That's why that people always be forming a TiO2 nanoparticle. TiO2 nanorod growth is very important for dye-sensitized solar cell application. This is a simple working mechanism. So that of a DSSC. So light absorption. So this is a LUMO, highest occupied molecular orbital, lowest occupied molecular orbital of dye sensitizer. So that when solar cell is incident, the excitation of the charge carrier to the low model of the dye, and then charge injection in the TiO2 nanorods. Instead of using a TiO2 nanoparticle here, if we use the TiO2 nanorod, the charge injection is very good from LUMO level of a dye to that of TiO2, and the TiO2 is efficiently charge transport to that of electrode, negative substrate, and then we are getting a maximum power conversion efficiency. So light absorption, charge separations, and charge escalations as a basic working mechanism. How that oxidation and reduction is takes place here, how that electrons are produced simultaneously in a dye sensitizer, and we are receiving a beautiful continuous current when we are using dye sensitized solar cells. So these are important components. The TiO2, why I put here is the TiO2 photon is playing a very important role in dye sensitized solar cells. ITO glass and TiO2 photoanode and NC dye, and then iodolite and then platinum cathode content. So quantum dot sensitized solar cells, there is also people are using a one-dimensional nanostructure. You see here how beautifully they are prepared one-dimensional nanostructure, and then quantum dots are sensitized on the one-dimensional nanodots. So how that co-sensitization. So two different types of quantum dots. So co-sensitized on the nanorod structure, one-dimensional structure of the anode. So photoanode, how the one-dimensional structure of TiO2 zinc oxide is useful in quantum dot sensitized solar cells also. So in order to achieve high photovoltaic conversion efficiency of quantum dot sensitized solar cells, that nanostructured TiO2 electrode is important. Sensitizer is important and essential. So that's why that advantages of semiconductors quantum dot as a sensitizer. Just here that advantages of one-dimensional nanostructure I put here, that well-defined crystalline structure, that unique optical and electrical property, and confinement effect. So one-dimensional structural morphology provides a charge carrier move freely along an axial directions, moving to confine in the transverse direction. The electron transporting photoelectrode comprised of a single crystal, even 100 times faster than that in the case of a nanocrystal. That electron transport, already I told you that in photoelectrode, instead of using a nanocrystalline thin film, nanocrystalline film, that one-dimensional nanostructure that is 100 times so faster as the charge transport. So that's why I always keen to see that change that one-dimensional nanostructure in DSSC as well as the quantum dot sensitized solar cells. So applications of one-dimensional nanostructure in different photovoltaic solar cells and photoelectrochemical cells, and light-emitting diode sensor and supercapacitor, etc. So thin film formation, generally the thin film deposition is based on the physical vapor deposition and chemical vapor deposition. So we need a high sophisticated instruments to prepare thin film of one-dimensional nanostructure by using a physical vapor deposition or the chemical vapor deposition technique. Maybe we will see that how we are preparing the thin film by simple solution technique. The film deposition generally by using liquid to film conversion, by using liquid that basically spin coating, dip coating, spray coatings are using gas phase to that of solid phase conversions. chemical vapor deposition and physical vapor deposition. In physical vapor deposition, generally we're using a solid material and vaporize it and then condense it to glass of any substrate. And then here in chemical vapor deposition, our initial reactions, initial materials are taken in the form of a gaseous gas, and then that is reacted on the surface of the glass substrate and then forming a beautiful thin film structure. So one-dimensional nanostructure preparation generally nanostructure generally classified into three-dimensional. Three-dimensional is polycrystals. We used to say the two-dimensional is nanofilm. Two-dimensional layer we used to call nanofilm, like a graphene. Two-dimensional property of that graphene. And one-dimensional generally used to say that the nanorods, nanotubes, and nanowires and zero dimensions of quantum dot structure. In particular, the one-dimensional nanostructure have attracted special attention due to the confinement of the other two-dimensional perpendicular to the longitudinal directions. That is the reason a researcher focused specifically on the one-dimensional morphology. It is highly useful for different applications, device applications. In this talk, I told you that I am just concentrating on the preparation of one-dimensional nanostructure of TeO and ZNO. Why we particular about TeO and ZNO? So of course, everyone is know that TeO and ZNO are large bandgap semiconductor material. So TeO2 generally used to crystallize in the three phases like anatize and rutile and brucite. And among various oxide semiconductor, titanium is a very important photocatalyst. It has a strong oxidation power and non-toxicity and long-term photostability of the TeO2. That's why people always using TeO2 as a photo anode in dye-sensitized solar cells. Then in zinc oxide, definitely that zinc oxide widely used in different applications, including thick film transistor, light emitting diodes, gas sensors, and transparent conducting electrodes, due to large broad strength and large excitation binding energy and high melting temperature. Importantly, it is possible to grow one-dimensional TeO2 and then zinc oxide nanostructure by control these conditions. So here in this talk that we have used that only these techniques, chemical spray pyrolysis for a seed layer preparation of the zinc of TeO2 and the ZNO, and the electrospray pyrolysis for seed layer preparation, pin coating and for a seed layer preparation. And then all first three is used for the seed layer preparation, and chemical bath deposition and the hydrothermal techniques are used for the preparation of the nanorod structure of TeO and the zinc oxide. These are all the schematic diagram of the deposition methods, like it is a chemical spray pyrolysis technique. So electrostatic spray pyrolysis technique, and spin coating and chemical bath deposition, and then hydrothermal method. So these two techniques are used for the growth of one-dimensional nanostructure of TeO2 and ZNO. So first three is used for the seed layer preparation. So interest. So just why we are interested to prepare that one-dimensional growth by simple solution technique. The one-dimensional generally nanostructure, one-dimensional nanostructured metal oxides to have a charge carrier transfer properties. I already told many times faster than that of nanoparticles. So owing to the higher diffusion coefficients. So therefore, in order to develop the TeO2-based nanoscale functional devices, so the control and quality of one-dimensional nanostructures are very important. So generally, one-dimensional earlier that they have prepared it by using traditional technique like a physical vapor deposition technique and sputtering and chemical vapor deposition, where that vapor, liquid, solid, and vapor solid transformations occur at a high temperature, so that they will use to get a beautiful high quality on that one-dimensional nanostructure, one-dimensional nanostructure. But those techniques are so we need a sophisticated instruments to prepare a one-dimensional nanostructure. So in order to change that, in order to simple preparation of one-dimensional nanostructure, that everyone should think about that simple solution techniques. The resulting nanostructures. We are always keep to prepare that simple solution for the preparation of one-dimensional nanostructure. These techniques are very expensive, and the mass production are very difficult by these techniques. So that's why that people always think about that simple chemical and solution technique. So first report they have in the literature, right, they prepared a single crystalline butyl TiO2 TiO2 nanorods directly on a FeO substrate using a hydrothermal method, and the size and number density of a TiO2 nanorods. So it will vary by changing the solution parameter, different parameter. This report opened the new door for producing a one-dimensional nanostructure on a conductive substrate at the low cost for making devices. So the nuclear layer, including FTK, IQ1 and FTO substrates, are used for the growth of one-dimensional nanostructure. So that FTO, IQ1 and FTO is layers are generally act as a seed layer for the preparation of one-dimensional nanostructure. But bare glass substrate is quite difficult to form a one-dimensional nanostructure. That's why people are always thinking about to prepare it on bare glass substrate using a simple seed layer concept. So in seed layer concept, that just we are creating a lattice mismatch between nuclear particles and butyl one-dimensional TiO2 nanostructure for the growth of one-dimensional nanorods. So it is challenging to grow oriented anisotropic single crystalline one-dimensional nanostructure on a seed particle layer coated with bare glass substrate. And seed layer thickness is a very important factor, and it provides a nucleation force and residual strain during the growth of the nanorods. So we have prepared more than 50 seed samples with various thickness using chemical spray pyrolysis and spin coating technique to optimize the growth conditions for growing one-dimensional nanorods. The minimum and different thickness, higher thickness and lower thickness of the nuclear layer have been optimized by spin coating and chemical spray pyrolysis technique. Maybe we will see in detail the driving force of the work. So interfacial energy, how that hydroxyl and oxide and dangling bond from the sea layer importantly play with the growing of particles from the precursor solution. Therefore, that involved to control the nucleation stage and the initial growth rate as well, and so that it is rationally we realized that this is a driving force for manipulating one-dimensional morphological structure quickly. So that so we are just prepared this this work. That this is the theme of that presentation. That exact one-dimensional TiO2 and ZMO semiconductors have been extensively studied worldwide, resulting in more than 25,000 publications in the year 2012. So the exact nucleation mechanism between seed layer and growing nanorods are still a matter of research. So maximum and minimum thickness of a TiO2 nuclear layer is optimized for growing one-dimensional TiO2 nanorods. So intentionally we doped the copper and M, how it is changing the TiO2, I mean zinc oxide nano and the micro rod arrays of the zinc array thinking on zinc oxide, the seed layer substrate. This is a bare glass substrate, and then TiO2 or zinc oxide seed layer, how on the surface of the TiO2 zinc oxide seed layer, how we prepare TiO2 nano, TiO2 as well as zinc oxide nanorods by using a simple technique. So according to that, that we conclude that overall conclusion part of the work is like that follow with respect to that of obtaining morphological structure of the deposited films. The interfacial relationship between the seed layer and the grown one-dimensional structure is classified as low and high and barrier and strong. Maybe we will see in detail one by one. So that our group they have worked with to control the one-dimensional TiO2 nano and zinc oxide nano micro rod. So for the different application point of view, this is the lengthy and the number dense single crystalline butyl TiO2 nanorods prepared by hydrothermal technique. So generally, experimental section TiO2 seed layer is prepared by spin coating. I told you like a simple chemical spray pyrolysis technique, and then TiO2 nanorods are prepared by the hydrothermal method by using a different temperature, like 180 degrees Celsius and 120 degrees Celsius. So and of lower size. What are the results we obtained is a lower size and number dense rotating to nanorocks. So generally, spin and spray coated samples, I mean seed layer, spin coated seed layer of thickness 30 nanometer and spray coated seed layer of thickness 150 nanometer. So used for the growth of a CO2 nanorocks. So the first one, how that we are getting a lengthy and dense rotating CO2 nanorocks on a lower and higher thickness seed layers. We will see this is the experimental section. PO2 seed layer prepared by spin coating thickness of 30 nanometer and chemical spray pyrolysis seed layer of thickness 150 nanometer. So using a hydrothermal technique, and then using those seed layers and lower thickness seed layers are prepared at higher temperature, 180 degrees Celsius. So we are obtaining that large size PO2 nanorocks, but higher thickness seed layer, somehow lower growth temperature. So we are obtaining a number density of nanorocks. So these are the XRD pattern of a grown CO2 on the nanorocks. So XRD pattern of this is a lengthy and this is a number dense nanorocks. So all the diffraction peak of nanorod is corresponding to the tube crystalline tetragonal rotile phase. So that so one extra peak observed at 25.4 degrees due to that of 101 plane corresponding to the anodized phase of in spray pyrolysis coated seed layer technique, seed layer nanorocks. So at higher solution temperature, higher solution temperature, 110 crystallographic plane could be exposed on the lower thickness seed layer. So under high growth rate owing to its high surface energy. At lower growth temperature, 101 preferential oriented crystallographic direction is induced on a higher thickness seed layer with respect to the lower growth rate. I told you that we are prepared at a higher temperature. So at higher temperature, growth temperature, so long size, lengthy PO2 nanorocks are formed. So growth rate is very high. But in a higher thickness seed layer and lower than growth temperature, so and number density, I mean number density CO2 nanorocks are formed on the surface of the seed layer. These are the HR10, HR10 and SAD pattern of a large size and number dense rotating nanorocks. This is a lengthy and the number dense nanorocks are confirmed by HR10, HR10 and SAD pattern. Lengthy nanorod lattice fringes with interplanar spacing parallel to the sidewall is about 0.311 nanometer. So it simply reflects the 110 crystallographic plane of the tetragonal rotary PO2 structure. So and also that lattice fringes calculations we have made by the HR10 images and confirmed that the length and number dense nanorod measured by HR10 images. This is a simple one-dimensional nanostructure record on the seeded glass substrate. These are the PO2 nanorocks grown on a spin-coated seed layer. So you see that length of the nanorods, I mean large size nanorods are prepared on the seeded substrate. The length of the nanorod is very high, but here you see the same seed layer thickness is high, that growth rate is low, but here seed layer thickness is that low, but the growth temperature is very high. So that the growth temperature in large growth temperature induce the fast growth of the CO2 nanorod. That is the reason that we are obtaining a lengthy CO2 nanorod. So, but here the growth rate is somehow lesser than that of the 180 degrees Celsius. So, but the thickness is very high. So that is the reason we are obtaining the number density of the nanorods are very high. So that on the surface of the seed of the substrate. So and then the cell images from the cell images and the length and diameter of the lengthy nanorods we have calculated is about 1.5 micrometer and then say 600 nanometer in the length and diameter. Then density of the lengthy nanorods density we have calculated it is about 3 to the power of 4 per centimeter square. And then and also the average diameter and the length of the number dense nanorods are about 150 and 600 nanometer. The lengthy nanorod length of the lengthy nanorods are 1.5 micrometer, but here the length is about 150 nanometer. So diameter is somehow similar, like less than nanometer. So and also we have calculated the density of the number dense nanorod is about 2.4 into 10 to the power of 5 per centimeter square. So the number density is different for lengthy TU nanorods and the number dense nanorod samples. So it simply reflects that number density is high in the um, uh, higher thickness seed layer prepared at the lower growth rate of hydrothermal method samples. So we have that analyzed that stoichiometry of the titanium and the oxygen at the 3 points of the nanorods, like the bottom, middle, and the top of the axis, top of the nanorods, by using a point and ID point selection of selecting the option of point and ID from the top view, so that oxygen, I mean, from that EDAX spectrum, the stoichiometry is confirmed, and then for a bottom and middle and top portion of the nanorods are about 30 is to 60. So we see that a different atomic percentage. And the same thing we have measured for the number dense nanorod. Also similar, almost the stoichiometry is retained at the top and middle and the bottom of the nanorods by using an EDAX experiments. So AFM images from the atomic force microscope images a large size and number dense rotating into nanorods. So that you see that two-dimensional, three-dimensional images. So this is a two-dimensional seed layers and two-dimensional, three-dimensional AFM images of the nanorods grown on the seed layer. So the height of the nanorod is calculated from the AFM is about 1.5 micrometer and the 600 diameter is that about 600 nanometer for the nanorods. So AFM images of nanorods are well, matched with that of SIM images. Then almost we observed the same results both in AFM as well as the SIM. UV visible spectrum, that how that band gap changes takes place, and then we measured it by seed layer as well as the nanorod sample. This is a simple UV visible absorption spectrum of seed layer. A and B simply reflects the seed layer, and A1, B1 reflects the nanorod samples. So that UV visible photons are passed through the TU to seed layers, and nanorods are recorded in the wavelength range of so 190 to 900 nanometer. So from the spectrum, it is clearly understood that band-to-band transition takes place. This is a characteristic of a wide band gap, the TU2 nanostructure. So we have observed a redshift of the TU2 nanorods as compared to that of a seed layer. This may be due to the increasing thickness and the length of the nanorod samples. So that marginal changes in absorption value of TU2 nanorods may be attributed to the difference in here. You see the marginal changes that may be attributed to the different in number of nanorods on the seed layer coated glass substrate, and then band gap value we have calculated from the top plane, and then for a seed layer as well as the nanorods. The band gap value is about 3.21 and 3.17 and the 2.95 and 3.01 electron volt respectively. So this is the growth mechanism that we have proposed after confirming so many parameters. So generally 4 facets of a TU2 one-dimensional nanostructure generated from 2D nanostructures. So therefore, it is possible to investigate different crystallographic plane growth of root TU2 nanorods by here we have done a lower thickness of seed layer subjected to the nanorod growth at a high temperature, and the higher thickness of seed layer for the subjected to nanorod growth at the lower temperature. And then you see here when the growth temperature is 120 degrees Celsius, the 101 crystallographic orientation is induced on the surface of the seed layer. At 180 degrees Celsius, a little higher temperature, so that what happened that 110 crystallographic orientation is exposed and induced the growth of a growth pattern of the TU2 nanorods. So the reason is the thickness of the seed layer desired that lattice mismatch with the rutile TiO2 and they generate a different crystallographic plane growth with respect to the growth temperature. So by simply controlling the parameters, growth temperature and seed layer thickness, so one can easily grow a different crystallographic orientations of TiO2 nanorods. So by this experiments that we just concluded that at lower growth temperature 101 crystallographic orientation is induced and one high temperature the 110 crystallographic orientation is induced. So just the conclusion of this work that we have successfully investigated a lower and higher thickness of nuclear layer on glass substrate for growing one-dimensional TiO2 nanorods by spin coating and nuclear spray pyrolysis technique. So we observed the two anisotrophic crystallographic planes for tetragonal rutile TiO2 nanorods grown along C-axis. The preferential oriented 110 and 101 crystallographic plane implies that TiO2 nanorods are standing randomly on the C layer coated glass substrate. Single crystalline nature and growth orientation of the TiO2 nanorods are authentically confirmed by HR10 and the SAD pattern. The light scattering effect of a charge carrier of a TiO2 nanorods is explained by using two visible absorption spectra. So the next work is nucleation energy barrier tailoring and the morphological structure evaluation from ZNO nano microrod arrays to microcrystalline films by N1 doping. So in this earlier case, we have optimized the seed layer, then thickness, and then seed layer, both seed layer as well as the nanorod growth by simple solution technique. We can, with respect to that of a parameter, growth pattern parameter, we can prepare a different orientation of TiO2 nanorods and also a different lengthy nanorods and number dense nanorods. With respect to that of applications that we can prepare our whether we need or any device applications lengthy means we can choose that optimized conditions we can go for it. We need a really more number dense nanorods and then so we can optimize the conditions. We can use those conditions for the growth and also orientation, particularly crystallographic orientation, also playing a very important role in different applications. If you want to know a different orientation of the nanorods samples, then you need to optimize the conditions, and then once you optimize the conditions for a different orientation, you can go for it. So by this simple solution technique, but earlier people used to prepare it by a sophisticated wafer-based technique, but by simple solution technique, one can easily control the growth pattern of growth of one-dimensional TiO2 nanorods and then orientation of the nanorods by simple controlling the parameters of the solution set. Another is instead of seed layer, we have just introduced the doping concept. So once doping is introduced, what happened really to the zinc oxide nano? How the zinc oxide nanorods are converted into micro rod arrays with respect to that of M1 doping? How the nucleation energy barrier is inducing the growth of a ZNO nano and micro rod arrays? We will see that one by one in this chapter. That experimental section that here that zinc oxide C layer is prepared by chemical spray pyrolysis technique. Instead of hydrothermal technique, here we have chosen a chemical ball deposition technique to grow a nanorod growth of zinc oxide. The growth temperature is about 85 degrees Celsius. So undoped and the M1 doped zinc oxide nano micro rod arrays are prepared by the simple chemical ball deposition technique. So these are all the results. For a pure sample, undoped sample, this is the same image of undoped zinc oxide thin film samples. Zinc oxide nanorods are vertically. You see that this portion that vertically beautifully standing on the seed layer. So the seed layer coated glass substrate indicates the footprint of the seed layer containing high density and homogeneously textured polar C plane nuclei. So that energetic surface of a specific crystallographic planes are tracer can easily find that place for sitting and bedding under epitaxial relations between the reactant solutions and seed substrate. Just we are just taking a seeded substrate and put the seeded substrate into that solution in the hydrothermal technique, so that how that solution and the seeded substrate playing an important role to induce the growth pattern of the nanorods and the microrod assembly. Length and diameter of the zinc oxide nanorods for the undoped sample is about 500 and 150 nanometer. So these are all the results, FESCM images of M doped ZMO nano microrod array statements. This is an undoped sample. This is a 3% M doped zinc oxide nanorods. This is a 7%. This is a D is 10% M doped ZMO nano microrod array statements. So the zinc oxide generally. Zinc oxide, in the case of zinc oxide, zinc oxide nano microrod arrays are generally grown by using the same experimental conditions. But once you add in the dopant, what happened that when the doping percentage is increased, when the doping percentage is 3, the diameter of the nanorod is nanorods are decreased and the number of microrods are increased. With the changes in the aspect ratio and the size, we have seen in the SEM images. Further increasing of the doping concentration to 7, the diameter of the nanorod is shrinking twice as compared to the undoped nano microrod arrays. So that this is a simply 3% doped samples. This is 7% doped sample C. That zinc oxide microrod is grown on the top of the zinc oxide nanorods. So the black portion is simply reflected. We have taken this image from the black portion. You see that beautiful standing, vertically standing zinc oxide nanorods. So that on the surface of zinc oxide nanorods, horizontally grown that zinc oxide microrods with respect to that of doping concentration. So there we have seen observing that density of the microrods grown on the vertically standing zinc oxide nanorods. So that in general, it is well known that the large scale synthesis of nano microstructure is very important for fabricating nano microelectronics. So the diameter and the length of the zinc oxide microrod grown on the surface of the nanorod sample is about 2 micrometer and 6 micrometer. The diameter is 2 micrometer and length is about 6 micrometer. When the doping percentage is 3, that I told you the diameter of the nanorods are decreased and number of microrods are increased, with increasing the aspect ratio on size, further increasing of M doping and concentration to 7. The diameter of the nanorod is shrinking twice as compared to that of undoped nano microrod arrays. So undoped nano microrod array samples at the diameter is about you see that 150 nanometer for M doping concentration. 7% of M doping concentration, the diameter is about 50 nanometer. So what happened finally when we increase the doping concentration to 10%? That zinc oxide nanorods are not growing on the seed layer coated glass substrate. So instead of zinc oxide nanorods, so completely, so zinc oxide microstructures are formed on the surface of the seeded substrate. So randomly distributed exotic microrods on the microcrystalline sheaf and spherulitic morphology over all the seeded substrate. So from this result, what we have realized that the interface energy is presumably playing an important role during the initial growth of films. So that's why that we classified that degree of supersaturation of the solution in the chemical deposition technique. So the degree of supersaturation is divided into 3 times. Then low degree of supersaturation, in intermediate degree of supersaturation, and then and high supersaturation. Low degree of supersaturation, it stimulates the heterogeneous nucleation on seed layer of a polycrystalline zinc oxide crystallites. So it is moving to lower growth rate. That is the reason we have observed a beautiful zinc oxide nanorods samples. It induces to form an edged hexagonal faces and thermodynamically stable prismatic zinc oxide nanorods, and which is subsequently elongated parallel to the C-axis. But when the supersaturation is intermediate, intermediate degree of supersaturation, horizontally aligned monodisposed ZMO microrod crystals are promoted on the vertically standing nanorods. So, but after, I mean, the growth temperature, I mean, growth time also we have changed from 1 hour, 1.5 hour, 2 hour, and 3 hour. So, but after 1 hour, what happened? The color of the solution is completely changed. That what happened? The solubility product between Mn and the Zn is different, and hence it simulates the different degrees of supersaturations in the precursor solution with respect to the growth time and the percentage of impurity ion doping. That is the reason solubility color of the solution is changed. But when the supersaturation is high in the solution, I mean at 10% of Mn doping, that supersaturation is intermediate and high. So if the supersaturation is intermediate means then completely microrods are randomly distributed on the serial substrate, and there is no growth of nanorods. So that so intermediate degree of supersaturation solution environment, microrods only randomly grow. In some places, the microrods are trying to build different microstructure, including a stelliform flower-like a structure owing to the oriented attachment of homogeneous precipitate. So due to that, a high degree of supersaturation. So fast crystal growth at high supersaturation degree induces the formation of spherulitic structure mostly over the microrods by interface energy tension. So it is found that the homogeneous and heterogeneous mutations on seed layer covered substrate under changing level of a degree of supersaturations by doping process in chemical bond deposition. So this is the AFM images of zinc oxide nanorod films. So in order to understand the growth mechanism of nanorods and microrods on seed layer coated glass substrate, so I told you that we have prepared a growth at different temperature, 1 hour, 1.5 and 2 on the 3 hours. So after 1 hour, then the sample is for 1 hour sample. That 1.5 hours sample. From 1.5 hour sample, we cannot take a from image due to high surface roughness of the zinc oxide microrod arrays. So we could not take AFM image at the different spots of the prepared sample due to that of high surface roughness. This is a confirmation HR10 and HR10 and SID pattern, growth orientation and single crystalline nature, and a hexagonal outside crystal face of the pure and Mn doped thin films confirmed by HR10 and the SID pattern. Zinc oxide has 3 types of crystallographic phases: a polar 0001 phase and 2 non-polar 2 1 bar 1 bar 0 and 0 1 1 bar 0 phases. These phases are non-polar, then 0001 phases are polar phases. We just confirmed it by the HR10 and the SID pattern. So this is for a undoped sample. This is for a 7% Mn doped ZNO nano microrod array 7 films. So in this case, we have observed some nanorods as well as a microrod also. So it just to confirm the orientation. So orientation changes. You see that orientation changes. Then maybe we will discuss in the XRE pattern. So this is completely, you see that 10% of Mn doping of the ZNO nano microrod array statements. So like a flower, star, and a sheaf, and the stelliform like a structures are obtained due to that of high degree of supersaturation. So it induces the, fast growth of the zinc oxide nano, the zinc oxide microrods on the surface of the seeded substrate. So completely destroy the nanorods growth. Homogeneous growth on the surface of the seeded substrate. So that's the reason that we are completely we are observed that the microrod arrays the thin films on the surface of the substrate when the doping percentage is 10%. So this is the XRD pattern of undoped and Mn doped ZNO nano microrod arrays. So you see this is the pure XRD. That you see the pure XRD orientation is 0002. When we increase the doping percentage 3, 7, and 10. You see the orientational changes. So beautifully, we observe that orientational changes and from 0, 0, 0, 2 to 1, 0, 1 bar 0 orientational change we have observed at high degree of supersaturation. So until that 7% somehow we managed to zinc oxide nanorods under the surface of the microrod samples, micro assembly. But after 10% of Raman doping, we completely observed that zinc oxide microrods are completely changing the crystallographic orientation from 0, 0, 0 to 1, 0, 1 bar 0. So that predominant 1, 0, 1 bar 0 crack reflection preferential growth along A and the M axis, and then drag reflection corresponding to the polar C axis and non-polar MEA planes in XRD is clearly released their strong orientations along a specific directions. Orientation means that 0002 is a preferential orientation until that 7%. So when we increase the 10%, then we have seen the complete orientation changes from 0002 to 101 bar 0 of a crystallographic orientation. What are the findings we have from the XRD pattern? From the XRD, we concluded that reorientation of the crystallites from 0002 to 101 bar 0. So it is occur 10% of M entropy. So that simply indicate that vertical standing C plane nanorod crystal growth is totally changed along M plane direction by experiencing compressive strain on the surface of the substrate. The reason is when increasing the dopant concentration, the higher computation between the two other host and impurity, the releasing of metallic ions from the complex, but does not allow for finding the nucleation site, vice versa on CDL substrate. So that during finding the sufficient amount of cations immediately produced in the reactant solution, that favors to change the degree of supersaturation from low to intermediate and the intermediate to high. As a consequence, that nuclear layer pointed to balancing the interatomic spacing value in this chemical solution environment. That's the reason that which facilitate the formation of interfacial energy barrier for the nanorod growth. So nuclear layer are just difficult to balancing the interatomic spacing in the chemical solution environment when the supersaturation ratio is high. So it's completely so that what we have seen is the interfacial energy barrier. That barrier is completely not allowed to grow the zinc oxide nanorods on the surface of the zinc oxide, on the surface of the zinc oxide layer. Hence, that horizontal aligned zinc oxide microrods, horizontally aligned zinc oxide microrods along the A-axis when the reorientation crystallites after is clearly understood that when the engineering and the crystal at low supersaturation degree, how the foreign impurity atoms not enter into the building the crystal growth that is moving to capsule finding of the post crystal plane from the solution under low growth rate. But what they are saying that under low doping, so doping, impurity atoms are entering into that crystal lattice of that is very less compared to the high doping. That is the reason that we are balancing to prepare the zinc oxide nanorods on the surface of the seed layer. But once it is increased higher, it's completely destroyed the growth of the nanorods. So here we have fabricated an exotic and the new surface morphology under degree of supersaturation with respect to that M doping. Under growth behavior is seen in the FESEM. This kind of a result obtained for the first time for the M doped is it a nano microrod techniques. And this interesting nano microrod micrometer size to nanostructure of the ZNO techniques is useful for the developing a future nano micro on the microelectronic devices. This is a UV visible from the UV visible spectra and the PL spectra of doped ZNO nano microrod is increased. So the absorption H is group shifted with the increasing of group concentration, simply indicate the enlargement of the energy bandgap of ZNO, nano micro arrays with the M doping application. The PL spectrum of a pure and M doped samples. So it simply exhibits the combined UV and the broad ultraviolet and blue and the green emissions. So from this work, we concluded that that role of interfacial energy between nuclear particle and nanorods by M doping is very interesting, and then we have investigated it extensively. So, with respect to that of mixed degree of supersaturation, the growth timing of the nano and micro rod are so analyzed by using an AFM. With respect to that of mixed degree of supersaturation, how we form the link of the nano and the micro rod arrays sample on the seed or substrate. So, with respect to that of a doping concentration, that how the diameter of the nanorods and aspect ratio of the micro rod changed. With respect to that of a doping concentration, when the M doping is a hard 10, the interfacial energy is fully confined between the solution and nuclear layer, and we're not allowed to throw the nanorods by intermediate and the high degree of supersaturation. It is also noticed that changes in surface morphological from the nanorods to the micro rod crystal structure at 10% of M doping. So it simply reorient the crystallize from C axis to the E axis of ZNO. So the presence of impurity state within the host ZNO nano micro rod arrays by M doping is characterized by the PL spectrum. This is another work, simple work about how that copper ions induce the reorientation of crystallites in zinc oxide nano micro rod arrays take place. But here also that we have prepared that zinc oxide C layer by air blast chemical spray pyrolysis technique, nanorod growth by chemical bond deposition technique. The growth time is 85 degrees Celsius. So again, we observed, pure and SU doped zinc oxide nano and micro rod arrays are prepared by this simple chemical bond deposition technique. These are all the sun images of a pure and copper ions doped zinc oxide nano micro rod arrays. So that you see here for the pure case, the black portion is nanorod array samples for pure hexagonal prismatic nano zinc oxide nano micro rods are developed by undoped samples. You see here that this portion is enlarged here. And beautifully that standing, vertically standing zinc oxide nanorods. So on the surface of the vertically standing zinc oxide nanorods, we have observed micro rods, horizontal micro rods on the surface of the vertical standing nanorods. It's a pure sample. After 5% of doping, so you see here after 5%, nanorod is converted into nanoplates. It may be due to that of a change in lattice Capstone values of nanorods. So then when the doping percentage is increased to 10%, that appropriate number of copper ions are entered into micro rod lattice sites and converted into your micro rod samples. And then 20% of 20 more percentage of copper doping into zinc oxide. You see that nanoparticle morphology, changing the preferential crystallographic plane to the different plane. We will see in the exotic pattern in area. So, from the surface analysis, just come to the conclusion that when we increase the doping, so how the morphological changes are happen on the surface of the seed or the substrate. So up to pure, then we will get a beautiful nanorod structure. So you see here that pure, pure we will see the beautiful nanorod structure, but when we increase the doping percentage, you see that the downside is the nanorods, vertical standing nanorods. That how the micro rods are changing with respect to that of increasing doping and that of copper. So completely micro rods are changing the micro nanoplate and then a microball structure on the surface of the ZNO nanorods may increase the doping percentage. So, and is a simple AFM images of the zinc oxide nanorods and the EDAX spectrum of a pure and doped zinc oxide nano microrod array statements. So, AFM images of here also we have used a different growth timing. So 1 hour, 1.5, and 2 hour, and 3 hours. So zinc oxide image of ZNO nanorods on the seed layer coated substrate. The growth time is about 1 hour from the EDAX. So just to confirm that on the composition of the chemical, so using an EDAX. So you see that how the crystallographic orientation is changing with respect to that of zinc oxide. So these images that EDAX is taken in the 1110 sample, crystallographic oriented nano rock samples. So that's why we put the 100002, 101 samples. In nanorods, and the 3 places we have taken the EDAX, and then we confirmed that stoichiometry of compound. From the XRD spectra, then you see here that the major peaks are observed for few ZNO, is 0002, but by doping 5% of copper and 10 and 20%, you see that crystallographic orientation changes of on the surface of the ZNO nano microrod arrays. So that that 100 orientation is completely dominant after the doping of the samples. After doping of copper, after copper doping, that we observe the orientational changes. This may be due to the changing of the structure from nanorods to the microrods. This is preferentially oriented is 002 crystallographic direction implies well crystallized nanorods along the C-axis. So that another preferential oriented 100 crystallographic plane reveals that ZNO microrods are lying along the EA axis. So that's simply these are from the XRD, then we just extracted some of the parameters. A UV visible spectrum, that absorption value around 400 nanometer is a characteristic spectrum of the ZNO structure. So we have calculated the band structure, band gap of the samples by a top line. So absorption value in the visible region is increased with respect to that of a copper doping. So which clearly reiterates that the transport and indirectly proportional to the copper ions in the nano microrod array statements. So this is that lower thickness. And finally, that I would like to give some summary about that one-dimensional nanorod structure. So lower thickness TO2 seed layers subjected to TO2 nanorod growth at high temperature, and then and also high thickness TO2 nuclear layer is subjected to TAO2 nanorod growth at lower temperature. So we have observed different patterns. So lower thickness sample with a higher temperature growth rate, high temperature growth, then we have observed a lengthy nanorods of a TaO2, higher thickness TaO2 nuclear layer, and a low growth temperature. So we have observed a number dense TaO2 nanorod sample on the surface of the seed sample. In ZNO, initially ZNO nano microrod arrays is grown on seeded substrate under the changing of the degree of supersaturation. We analyze the degree of supersaturation. So degree of supersaturation is low, and the intermediate, and the high. The high is divided into that a barrier and a destroy. So that if a low is if a degree of supersaturation is low, then we will observe the beautiful nanorod structure. Some intermediate mean that we observed that microrods on the surface of the nanorods. So when the degree of supersaturation is very high, it completely destroyed that nanorod structure. So what we have observed, only microrod on the surface of the seeded substrate. So further increasing of that higher supersaturation, so we will get a different structures of microrod samples. So, on the same way, like a copper, when they're using a Mn and copper doping, how it is changing the degree of supersaturation, how it playing a very important role in the interfacial relation between a nuclear seed nuclei and the growing nanorods. and how it is destroying the morphological structure with respect to that of changing the degree of supersaturation, and also that interfacial energy between the nuclear layer and the nanorod samples. So with that, I would like to stop. Then this is the result that we have taken. And with that, I would like to stop my presentation. If there is any queries and clarification, please.
Yes, thank you, sir.
Thank you.
Dear
Any
professors,
questions?
if you have any questions, please unmute and ask your questions.
Any queries? Any questions, please?
If you have any questions, please post in the chat box.
ஆக்டிவிட்டிஸ் இல்ல டிபார்ட்மெண்ட்ல நாங்க வச்ச எல்லா ஆக்டிவிட்டிஸும் வந்து
We'll wait a few more minutes, sir.
So good morning, sir.
Good morning.
Sir, I'm Dr. N. Umar Shankari from SFR College for Women, Department of Chemistry, sir. Sir, how does the surface oxygen vacancies, they play an important role in the solar cells?
I don't know. Actually, you are asking about surface oxygen vacancy. Of what, where, what?
So whether they play a role in as a hole scavenger or electron scavenger?
No, actually, I missed the talk that we have used a seed layer, and then oxygen vacancy means where it is an oxygen vacancy that time.
Sir, we are upon the FTO, we are coating a seed layer now, sir, with the metal oxides.
Okay.
Those metal oxides may be formed with these kind of oxygen vacancies.
Yes, of course. That seed layer, actually, here that role of seed layer is to induce the nucleation and the orientation of the nanorod growth with respect to that of degree of supersaturation in the solution, hydrothermal solution or chemical bond deposition solution. So, nanoparticles are with respect to nanoparticle growth and also growth rate of the growth rate temperature. So whether the growth rate temperature is very high means that we have observed the fast growth rate. So we are observed that lengthy nanorods in TO2 phase. But CO2 nuclear layer and how it is initiate that TO2 nanorods with respect to the degree of supersaturation. There is no. I don't understand the oxygen vacancy here.
Sir, I have one question, sir. Not questions.
Yes.
So, any basic methods?
So,
Procedures to grow the nano particles and nanostructures for solar cell applications, sir. Easy method or low budget method, sir?
All
For startup.
methods, all methods are very low cost method only. That's why I just even during my presentation I told because simple hydrothermal technique that hydrothermal pump is uh, hydrothermal pump cost is about 10,000 rupees.
Okay.
And chemical bath deposition setup is very simple setup. There is the procedure is because we prepared that nanorods on bare glass substrate. It is very difficult. Nanorod structure by powder nanorod structure is very easy, but thin film nanorod structure is very quite difficult. By using a simple solution technique and then controlling the growth parameters of the solution, then we will prepare a beautiful nanorods on the surface of the glass substrate. So glass substrate, before using a glass substrate, and then we prepared a seed layer. That seed layer will induce the growth of the nanorod structure with respect to the degree of supersaturation of the solution. That nanorod growth is simply by the hydrothermal technique as well as the chemical bath deposition. Both techniques are very simple technique. You can use it in a laboratory very easily. Instead of getting the same cave to nanostructure by using a physical vapor deposition and chemical vapor deposition. PVD, CVD, we need sophisticated instruments to prepare it. But this is a very simple, low-cost instrument and a solution technique.
Yes, sir. Thank you, sir. Another question from participant, sir, from Venkatesh P. Dear sir, thank you for wonderful presentation. The zinc is in +2 oxidation state in Z and O, and the respective dopants may have different oxidation states. Hence, apart from manganese and copper, which metal dopant may particularly suit for the zinc, sir?
Okay, so actually, people are choosing a different dopants randomly, but oxidation with respect to that of oxidation state, generally they have reported in literature. They have reported metal dopants, iron, copper, etc. With respect to that of dopants with the different oxidation, yeah, oxidation state. No one generally not choosing that with respect to that of oxidation state. In some part they have using to choose for with respect to oxidation state. Generally, once it is coincided with the Mn copper, we found that Mn copper as well as the other dopant. So all are we analyzed it by that copper, Mn, etc. But generally, all dopants are metal dope. Generally, people used to do that doping by the metal. Oxidation state, a slight modification they have observed, but for the nanorod growth, we have analyzed that Mn and the copper is the best suited one for the zinc oxide. That's why that we have chosen a Mn and the copper.
Okay, thank you, sir. I hope the answer is satisfied with the test, sir. So, any other questions? Please unmute and ask your questions. I hope there is no questions, sir. Shall we end up, sir?
Okay. Okay, sir. Okay, thank you.
Dr. Hari Krishnan.
Sir,
Yes, sir. Proceed.
yeah, unthankful is no mercy, but the thankful heart will find in every hour with heavenly blessings. A warm and wealthy noon to our most honorable chief guest, management committee, delegates, my dear friends. It's my privilege to propose a vote of thanks and acknowledge the contribution of effort posed on the second day of 7-day faculty development program on recent trends in solar cells. On behalf of the entire fraternity, first of all, my sincere thanks to Almighty God for making today's event a knowledgeable manifestation. By His blessings and grace, we are able to make the event what it was. On behalf of the organizing committee, I extend a hearty thanks to our chief guest, Dr. Ramalingam, spared time from his busiest schedule to grace this occasion. Today, we have an opportunity to hear your thoughts, and this will surely be going to encourage us in various aspects. Your thoughts have enlightened our minds and shown us a new path. Thanks for sharing your knowledge today. Thanks a lot, sir. A special mention Okay, sir. A special mention to our respected principal, Dr. Mutmani ma'am, for being the catalyst that stimulate us to do our best and standing as pillar of strength. With a deep sense of appreciation, we thank faculty members of various institutions for their untiring effort. Last but not least, a big thanks to each and everyone who have made this event possible. Thank you one and all.
Dr. K. sir.
Yes,
Sir.
sir.
Sorry for inconvenience, sir. Thank you, sir. Thank you very much, sir.
Thank you, sir. Thank you, sir.
Sorry, sir.
Thank you.
Dear participants, today no quiz. So please bring the feedback from tomorrow session starts at 10:30.